Hey, today I'm going to talk about genetic algorithms. So, what are genetic algorithms exactly? Well, genetic algorithms is actually a branch of a greater concept called evolutionary algorithms. It basically states that if you can represent solutions to a problem, then you can evolve solutions to that problem by copying natural evolution. So, to understand this concept better, we will take the knapsack problem. This problem is commonly used while explaining genetic algorithms. The knapsack problem states that you have a bag and there are items, and each item has a value and a weight. What you want to do is take as valuable items as possible into the bag without going over a weight limit. Let's take an example of the knapsack problem. Let's say we have a weight limit of 15 kilograms and we have 4 items. What to do is get as valuable items as we can without going over the weight limit of 15 kilograms. Next, we want to find a way to represent solutions to this problem. We can represent solutions to this problem by using 4 bits. Each bit would represent an item. Bit means either a 1 or a 0. If the bit is 1, then we take the item to the bag. If the bit is 0, then we don't take the item to the bag. Then we need a way to determine how well a solution does. We will call this process fitness function. The fitness function takes a solution and determines how good a solution is. The fitness function for this problem can be this. Calculate the sum of all the weights we put in the bag, and if the weight goes over the weight limit, then the fitness function returns 0. But if it doesn't pass the weight limit, then calculate the sum of the values, and that will be the return value of the fitness function. Let's apply our fitness function to an example. Let the example be 0101. So we take only the second and the fourth items to the bag. The second item has a weight of 2 and the fourth item has a weight of 9. If we add these together we get 11, which is not over the weight limit. So we take the sum of the values. The values are 4 and 2. If we add these together we get 6. The fitness function returns 6. 6 is how well the solution does. 6 is how fit the solution is. But if we apply the fitness function to 1101, then we'll pass the weight limit, because 7 plus 2 is 9, 9 plus 9 is 18, which is over the weight limit of 15 kilograms. The fitness functions return 0, which means the solution is useless. Next step is evolution. The goal is to get the fittest solution possible. Darwinian natural selection has 3 principles: variation, heredity, and selection. First we start with variation. Variation means that you have entities, solutions in this case, of different properties. Properties means bits in our case. The pool of entities is called a population. And variation is the state that there are different solutions in a population. We can create a population randomly to start with. Once we create a population randomly, we should also calculate the fitness score of each solution. In nature, this is equivalent to how probable it is for the entity to survive and to pass its genes onto the next generation. In our case, the fitness function is for how well the solution does. Next stage is selection. Selection means that we need to select one or more solutions which will be parents of the next generation. In our case, we can select these parents as the fittest ones. In your simulation, you can choose to select only one parent, but you have only one parent, you can do the crossover process and you have to use mutuation. In this example, we take two parents so I can show you both the crossover and the mutuation processes. Let's define the fittest two solution as the parents. Now, we are on this third stage, which is heredity. Heredity means generating a new generation out of these two parents. First, we can apply the crossover process. Crossover process means something like take the first 2 bits of the first parent, the last 2 bits of the second parent, then you can have a new entity for the next generation. Or something similar can apply, like the first and the third bit with the second and the fourth bit of the other parent. After we generate this new entity, we can use mutuation to generate new entities for the same generation, because the population of the new generation can't include only one solution, because we will need competition. So what we can do is we can use mutuation. Just copy the entity 8 or 10 times or how much you want and apply mutuation to them. Mutation rate is usually really low, something like 0.005, and you go over every bit, and by chance you change the bit to, if it's 0, you change it to 1, if it's 1, you change it to 0. And then you will have unique entities without ripping apart the genes from the parents. So they will be related to parents, but they will be different from each other too. What you'll have after this is a new population. So you can go to the first stage of variation and do the process over and over again. As time passes, you will get fitter solutions, and that's why you should continue doing it for a long time. This is how you get a fit solution for a problem using genetic algorithms. Thanks for listening.